I'd like to say a big thank you to our sponsors, Talent Insights. Talent Insights are Australia's leading specialist data recruitment business. With offices in Sydney, Melbourne, and Brisbane, they're expert at providing recruitment strategy and building data teams for clients across industries Australia-wide. They provide recruitment solutions for all roles across the data lifecycle, including data engineering, data science, advanced analytics, customer and marketing insights, business intelligence, data product managers, and data governance. They're skilled at finding the best permanent and contract hires for your business needs, as well as statement of work, project focus, data resources. At Talent Insights, relationships matter most. I can say from first-hand experience, Talent Insights are fantastic to work with. Whether you're a business leader within an HR network or a specialist data candidate, Talent Insights should be the first company you turn to for all your data recruitment needs. Find them at talentinsights.com.au.
Hi, this is Felipe Flores. Welcome to Data Futurology. Today we have a super exciting episode. We're going to be discussing graph analytics, and we've had a lot of questions to cover this topic, so we're going to dive deep into it. For that, we have David Bader. David is a distinguished professor and director for the Institute of Data Science at the New Jersey Institute of Technology. David, thank you so much for joining the show. How are you going today?
I'm doing great. Thanks for inviting me. Just love talking about graphs, so this should be an exciting time.
Oh, mate, I'm so excited to get to spend some time together, to pick your brain, and to, answer a lot of the audience questions that we've been getting on this topic, which is phenomenal. So before we get started, can you tell us a little bit about your role and your remit, the type of work that you're doing and focusing on at the moment?
Thank you. So at the New Jersey Institute of Technology, I lead a research institute called the Institute for Data Science. And right now, let me just tell you about one of the exciting projects that we're working on. It's a open source, large scale data science framework called Cuda. And this is on GitHub. You can search for Cuda is the Greek word for bear, Arkouda. And we're building out graph analytics at scale. And what we're doing, to me, this is so exciting. We're creating a productivity front end so that anyone from their Jupyter Notebook and Python can call our framework. But in the back end, you can have a supercomputer running on tens of terabytes of data. So for me, this is quite exciting to democratize data science and especially graph analytics so that anyone with a problem and who knows Python will be able to work on some of the largest and most challenging data sets.
Amazing. So keen to explore that. Definitely to explore that further. But tell me, how did you get started in the graph space? How did you get interested in focusing in that area?
So my work in graphs goes back almost 40 years. I've been just fascinated with graphs for even before I was in school. And that just goes back a long time, if you will. And I like graphs because they show connections and relationships. And for instance, vertices in the graph are points and lines in the graph are edges. We could build surfaces or groups or do a lot of things with graphs. So very early on, I was very interested in looking at large graphs and graphs that abstract from the real world, whether it's a transportation network or whether it is trying to understand network security, or whether it's a friendship network on a social network platform. And so for me, graphs have gone from being a niche to now being mainstream, where most organizations have graph problems and look for graph analytics that can solve their problems in the enterprise.
Yeah, that's really great. And how do you feel the say graph graphs maybe as a capability? How has it evolved over time in terms of the there's this, I guess, the mathematical theory side, there's the technology side, and then there's the industry applications. How has the different parts of the capability evolved in the time that you've been interested in the space?
What has happened is that many organizations have realized that some of their most challenging problems are amenable to graph analytics. So if you think about a graph, it abstracts relationships between objects. And those objects could be people, the objects could be computer IP addresses, the objects could be nodes in a road network. And so any problem that we can abstract where we have relationships between objects, we could use graph analytics to solve. And then once we can map a problem into the graph space, we think about what are we trying to find? Are we looking for paths? For instance, the shortest path between friends from me to you in the graph? Are we looking for communities? So is there some emerging community of interest? Are we looking for influencers? And so these are the types of questions that we often have once we're in the graph domain. And what I like to do is design new scalable algorithms that are able to work on these ever increasing large size graphs to solve the analytic that we're looking for.
Mm-hmm. Yeah, that's really, really interesting. And what are some of the applications that you've seen over the years or maybe recently?
There are many applications. For instance, we are working right now with Accenture on trying to detect malfeasance within the open source community. So if we think about open source software as a supply chain, then we are looking for compromises of that supply chain. And we've seen last year some hacks like Log4j and SolarWinds that infected large organizations based on the open source supply chain of software. So we're using graph analytics to analyze the open source software to try to detect these types of very defined intrusions into software. But we can also use graphs to understand, for instance, patients and electronic health records to understand better treatments and even personalized medicine through graphs. And we can also use graphs to understand our electric power grid. So to shore up and make more resilience the power that runs our telecommunications, our food production, our transportation, and more. And so graphs, we find many, many applications through many domains that makes it a really fundamental tool in our toolkit.
Oh, mate, some of those applications are near and dear to my heart. I work in healthcare, so I'm a CDAO in a health tech business, and obviously looking at patient data, looking at the different doctors and providers that people can go to, and seeing how they travel through the healthcare industry, and that's obviously super interesting for us, and also what leads to good outcomes and better outcomes, things that we're looking at. The other one around, cybersecurity, information security, looking at the patterns. So information security and cybersecurity is within my remit at work. So something that I spend a fair bit of time thinking about as well. Recently, there's been a lot of attacks in Australian organizations, larger Australian organizations as well, like Optus, and which is telecommunications business, and Medibank being a large health insurer here. And before this, I worked in finance, where graph has come up as well in understanding customers, understanding the movements of money, how accounts are linked and people are linked, and the relationships there. So it's such a widely applicable capability. What would you say to people looking to get started in applying this capability to the problems that they might be facing in their organizations?
So that's a great question. So for instance, let me take an example that you mentioned in the finance sector. Maybe you're an organization that's trying to detect fraud. And so what you may do is create a network, for instance, every time a customer purchases an item at a particular location, you start to build up a graph with all the nouns in the system. So a person would be a vertex, a item that they bought would be a vertex, and you could have attributes such as the geographic location. And through all of these transactions across all of your customers, you would start to build up a very rich graph of information. And then in that graph, you may look for outliers. So do outlier detection to try to find fraud within that network. So the first thing that you would need to do when you have a problem is think about what is a vertex and what is an edge. So I like to think about vertices as nouns or objects in the system and identify what they are. And then for a graph, I need relationships between those objects or nouns. And those are sometimes represented as verbs or relationships between those objects. So once I've defined from my problem space the abstraction of a graph, now I'm ready to think about what type of graph is it? Are the edges directed in one direction, or are the edges undirected? Are there timestamps as to when I see a vertex join the graph? Are there weights on the edges? Are there weights on the vertices? And so I can go from my very rich problem space and build up a graph that represents that abstraction. And then once I have the graph, I have to map the questions that I have into the graph analytic space. So really the first step is just thinking about that graph. What is that graph going to represent? And then the manual work of ingesting my data into a framework that can build that graph. And I should say there's many easy to use frameworks out there. In Python, we have NetworkX, there's Neo4j, and other packages out there that very easily let me ingest data and form a graph out of that data. But when the problem size gets to be very, very large, and I'm talking about billions of vertices, that's where I come in with some massive graph solutions.
Amazing. And how do the algorithms change when we start thinking about and being in the world of massive graph solutions?
That's a great question. So often graphs have missing information. For instance, if we have a graph representing our network traffic for a cybersecurity application, we often will miss some things or get some things wrong. And we have to understand that the graph isn't perfect, but it's the best that we can do to represent that information. Oftentimes, we get false positives in our analytic routines. For instance, we're looking for a cybersecurity intrusion, and maybe 1 in a million times, a flag gets raised that we investigate and find out that it wasn't a real attack. Now, that's okay when your problem size is small enough. 1 in a million, you or I could look at, maybe we get one of those once in a blue moon and realize whether or not that was an attack or not. But when we start talking about massive graphs where we have trillions of edges in the graph, 1 in a million error rate will start to overwhelm us. So what we have to do when we're designing new graph algorithms is have more fidelity in the algorithm to make sure that the false positive rate is maybe 1 in a trillion versus 1 in a million. So that's one of the challenges that we have as we're designing new scalable algorithms.
And when you say that, I guess my follow-up question is, can you tell us more about how to increase that fidelity? My mind would initially goes into data quality, better, more data acquisition, things like that. But I'm sure there's advancements on the algorithm side that are helpful as well. So how do you increase the fidelity of the algorithms?
So that's a great question. Often many of our graph algorithms that we're trying to compute are very challenging or very costly to compute. And so we look at better hardware, better processor designs. We work with many companies over the years like IBM, Intel, NVIDIA, AMD, and others to design better processors and better accelerators so that we can scale to these larger problems and run the more effective algorithms to solve the problems that we're looking for. So often in the algorithms, we may take a shortcut in order to solve the problem, but if we can remove those shortcuts and solve for what we're really looking for, then we may get better fidelity in that solution. So there's many techniques that we use, and we try to scale the algorithms up. We try to use more cores, more threads, and more processors in order to speed up the algorithms that we want to solve. They're often very time-consuming to solve these large graph problems because the architectures become very challenged when we're doing memory-intensive operations like walking through a graph. And so some of that are the new algorithms that we've designed to speed up those calculations, to better partition graphs, and better to have some very complicated kernels that run on those graphs.
Yeah, really nice. So hardware improvements is one side, then the computational component and managing distributed computers, distributed networks to be able to do the computations required. And then obviously there's the data side, where you're thinking more about how to crunch information at that scale, which is massive.
So let me give you an example from a paper that we just put out. Oftentimes, it's very hard to find communities in large graphs. The graph looks like a big hairball, and it's hard to look at it, observe it, and pull out a community. And one surrogate is looking for dense subregions of the graph where a lot of triangles exist. And a triangle is three edges that connect three vertices together. We all know what a triangle is. So we want to find parts of the graph where we have more triangles than other parts of the graph. And so triangle counting and finding is very hard to do in parallel. In fact, most of the algorithms today are brute force. You look for triangles by finding a wedge, and then you send that wedge around to see if anyone else has the closing edge to it. So it just generates a lot of communication. Recently, we just found and designed a brand new algorithm that does it in a very different way, reducing the work and the communications by really just identifying the triangles in a more direct approach rather than swamping the computer with a lot of these partial triangles floating around. So we're very excited because it's communication optimal, that we found a new algorithm and a new way of doing it that we imagine will now catch on as the predominant way to find triangles and thus do community detection in these very large graphs.
Phenomenal. Like that's such a powerful capability with applications across so many industries from fraud to healthcare to electricity, as you were saying, utilities. That's outstanding. How long was that work in the mix? Or then how long did it take to be developed?
So we did that work this summer with a couple students. I have some fantastic high school interns, as well as some great PhD students, master's students, and undergrads. So during the course of several weeks or months, we talked about it and then had the aha moment of, here's a better way to do it. So we actually wrote the algorithm probably about 3 times, taking what we had, throwing it away, figuring out a better way to do it until we arrived at this brand new algorithm. And it's elegant. I love it because it uses some kernels like breadth first search, and then it does a sparse matrix transpose, and then it does a broadcast. So it's very simple to describe and really simplifies the work that's needed to find triangles in a large graph.
I love it. That is great. And did you say there was high school students in the team?
There were several. So I had 2 or 3 very fantastic high school students who worked on that and are co-authors on the paper that we put out.
Amazing. Imagine doing that type of work while you're in high school.
We
That is
have
phenomenal.
some great students in New Jersey, and for the high school students, they may not have been able to understand all the depth of computer science, but they were able to work on the algorithm, create a prototype in Python, and actually help me diagnose better ways to implement the algorithm through their work. So they were fantastic and integral to this work. So I really love having a diverse group of students, and from high school all the way through PhD.
Amazing. Amazing. That is phenomenal. And tell me about your new book, Massive Graph Analytics. Tell me love it. Yes, I've got a copy as well. It is fantastic. Tell me what were you aiming to bring to the world with the book? It's such a big project. It definitely takes a lot of dedication and consistency. So I first of all, congratulations on producing this book. And tell me what was the some of the aims on what you're wanting to bring to the world with the book?
Thank you. I appreciate that. And it was a lot of work. Many years went into this book. My vision was to have a reference on the top work for this really emerging area of massive graph analytics. So as the title of the book says, it's Massive Graph Analytics, where I collected up over 85 contributors to the book in 21 chapters that are partitioned in sections on algorithms and applications, solution frameworks, so that anyone who is interested in this field, from a novice to an expert, would be able to have in one place all of the top research and studies related to massive graph analytics. So we are really proud of this book, and it was just a phenomenal experience to bring together all of these contributors. As I mentioned, over 85 people contributed to the work. And this is the first book on the subject. It's the one place, one-stop shop in order to learn everything about massive graph analytics. So I'm really proud of it. And I think I learned a lot as well reading these chapters and also writing the introduction for the book, where I was just fascinated about where did graphs start? Who was the first person to use a graph for a real-world graph analytic problem? So there's some nice stories in the introduction, but I think there's a chapter in there for everybody.
That is phenomenal. And given that it's an emerging area or a new area, how did you structure the book? How did you think about giving an overall structure to something that's new and developing so quickly?
I've been in the world of graphs, as I mentioned, for almost 40 years, but I've been working with collaborators on large-scale graph analytics for many years and invited a number of those authors to help with the vision and the content for the book. So I really thought about what does it take to know everything about massive scale graphs. And this book, as you know, has almost, I think, 601 pages. So there's a lot of material in this book. But I thought about what is it that you need to know in order to know the mathematics of graph analytics, to know the implementation of graph analytics, and to know solutions that are out there and applications that are currently being solved. So I tried to fit that all in a natural way in this book so that there are sections of this book that are going to be relevant to anybody interested in graph analytics. Now, you may say, I have a small graph problem today, but what I challenge you with is anyone with a graph problem. As we know, data keeps increasing at an exponential rate. So anyone who thinks they have a small graph problem today probably tomorrow we'll have a massive graph analytic problem. So we'd like to think about what do you do once the problem no longer fits on your laptop, once you have to figure out how do I solve this problem when I need more than my laptop and my Python routine is taking too long. This has to run instantaneously and it's taking me hours. What do I do now? So this is a solution book for anyone who is thinking about graphs in the enterprise and moving towards large scale.
That is outstanding. I can't imagine the amount of work to make this all happen. So I'm so impressed. What were some of your I can't say favorite, because like with a book, it's all your labor of love. But what were some of the areas that maybe piqued your interest as the book was being written and forming?
So I love all 21 chapters. They are all fantastic. But there are chapters in there that really are just fantastic chapters. For instance, some researchers at MIT have some new graph algorithms that I think are quite exciting to read about. We have some companies that contributed chapters. For instance, Neo4j has a chapter in the book. And we have new application frameworks. As I mentioned, our work with our Cuda is a chapter in this book. So I think that whether you're an academic or you're in a lab or working at a company, you'll find chapters that are very relevant. Whether you're on the research front or whether you're a developer, you'll find some material that's very useful in the book.
Yeah, I thought it was really good to include, applications and frameworks that, as well as the theory and software. It really covers so many different areas. And could you tell us a little bit more about our Cuda? How's the trajectory been so far? Where is it at now? And then we can go into what's coming up next for our Cuda.
Sure. So our Cuda is a project that was started by the US Department of Defense just about 2 years ago. So it's an open source framework. It's on GitHub, so anyone can clone a copy of it. And we were really interested in finding a way that our data scientists, whose lingua de franca is Python, could take the productivity of Python, but get the performance of a supercomputer in the back end. We wanted to democratize data science. So what we do as developers, myself and my research group, is that we design new algorithms that are incorporated into our Cuda. We do all of the complicated work under the hood so that a user can call from Python a routine similar to NumPy or Pandas, but have it operating in a backend supercomputer and getting the near real-time response time that they're used to when they're just running in a Jupyter Notebook on their front end. So this framework, I think, is the first of its kind. And we are operating on data sets that have, say, tens of terabytes of information in the data set. We're also building out native graph analytic routines so that a user who views their data as a graph will be able to call graph algorithms like breadth-first search, connected components, K-truss analysis, Jaccard coefficients, triangle counting, and more, and have it work in near real time. You click enter and you get your result right away. And all of this is done through the hard work of scaling these algorithms for that back end. Now, I should also mention on the back end, we're using an open source compiler called Chapel that was developed over the last 20 years from Cray, which was acquired by HPE. So it's a product from HPE Cray that is just this fantastic open source compiler. So the entire framework that we have is open source, and we encourage others to pick it up, use it, kick the wheels, and to develop and contribute back to this open source project.
Amazing. And what type of infrastructure will people need to be able to run our Cuda and get into these type of problems?
You can run this on any system you have. So Chapel could run on a laptop, it could run on a cluster, a large multi-core machine, or a big supercomputer, one of the most capable in the world. So depending on the size system that you want on the back end, or high performance. It could be everything from a cluster to a big, massive supercomputer. And so there's no other requirements, just having your systems that you want to use, the storage on the back end to store your data, and have the curiosity to be able to want to run analytics on some of the largest data sets that you have within your organization.
Phenomenal. And what would be your vision for Cuda? What would you love for it to become?
Right now, we have tens of users, so we have early adopters who are finding fantastic uses. In fact, just yesterday, I heard a story of an intern who picked up our Cuda and analyzed a data set that hadn't been analyzed before, did a couple queries, and found a problem with how the data was being collected. They were missing some information. No one would have ever suspected that unless you could have run, and I'm told the intern ran a query in 5 minutes to be able to identify issues with the data that was being collected. So these are the types of use cases for our Cuda when an intern in 5 minutes can discover things that you never would have guessed without having this just superb capability to understand massive data sets, including graphs.
Amazing. So that is phenomenal. I love that story, that for a new person to the organization to be able to come and find insights and add value so quickly to improve the organization. So it's definitely a massive uplift in the capability that people can have by picking up this tool set. And where what would you like if you look into the future? What would you be excited for Cuda to become or to be able to do? What is in your vision for it?
What I'd like is every single person and organization who has a massive graph analytic problem, a large graph problem, or a large data science problem has the capability to solve it no matter where they are in the world. So I want equitable access for everyone to be able to work on these problems and to find new discoveries that are important and help solve global grand challenges. I think that we have many issues in the world today, and if we give more capabilities to those with data and let them empower the data, we'll make the world a much better place. So that's really my goal and my vision, and I really hope others will join in and help with this work.
I love it so much. I think that is a wonderful ambition, and I think also an excellent note to end on. David, I want to thank you so much for your time, for your contributions, for all your work, for the dedication to be able to help bring this quality of important work to reality, and to help disseminate the knowledge in a way that is accessible and can make a difference around the world. Thank you so much for your time and for all the work that you do.
Thank you so much. It's great to talk with you, and I encourage everyone out there to look at the world as a graph. And this is just a fantastic time to do so. So thanks to you and to all of your listeners.
Thank you so much.
Thanks for watching this video all the way to the end. I hope that you got a lot out of this discussion. And if you're watching on YouTube, please like and subscribe to the channel so more people can find out about the challenges that leaders have in the analytics and AI space. And that's what we're trying to share in Data Futurology. So please like and subscribe. And if you enjoyed today's episode, please tell your friends. Thank you so much.